This is example number one for forces acting on a general body. In this particular example, we have an aircraft that has a weight of 10,000 pound forces uh, and is flying at a level flight of 150 miles per hour. The air density at the height, at the altitude where it's flying at is given. The total wingspan is 100. The circulation associated with the wing and trailing vortices are related to the velocity, uh, is related to the weight, and the weight is actually going to equal to the lift, and is given by this equation. And actually given by this equation, so you can understand, since this will be a finite wing, right? So then you will go minus b over 2, b over 2, gamma, if you remember the equation that we had, dz, okay? So then this will give you b times this k, okay? So when you integrate, that's where this b comes from. The Rankine model, use the Rankine vortex model, if you remember, to determine how fast the trailing vortices are moving downwards. Um, and typically, your trailing vortex separation is about 80% of the wingspan. So let's see how we will solve this problem. The problem is not really complicated. What we are really trying to really understand is what is the speed right here, okay? So we want to find what is this, how much is this speed going downwards. Okay, this is looking at the aircraft seen from this side, okay? So you got trailing vortices, and this is pushing inward, outward. So if I really look at this, I am looking at the airplane maybe like this. Okay, and you are trying to evaluate that at about 80% of the span. So the question is, how much is the speed of the airplane actually trying to, how much this downward velocity is? So first of all, if you remember your for your circulation, okay, this comes from the problem itself, right? It says L is equal to rho v infinite times b times gamma. Then from here, I know what is my circulation value. My circulation is given by this equation. So, and if you remember from the Rankine vortex model, it says that your speed will be gamma 2 pi r. Okay, so r in this case will be the distance from here to here. This is your r. So r will be 4 over b over 4 over 5 times b. Your gamma is given by this equation. So your velocity at 1 and velocity at 2, that which will be the same, will be, if I do a little bit of mathematics and replace everything in here, so I have 1 over 2 pi 4 5b, and L is L over rho v over b, okay? To a little bit of math, you can show that a v1 is equal to v2 with 5 times L, 8 pi rho v infinite b squared. So replace the values. I know that because it's level flight, L is equal to W. This is 10,000 pound forces. 8 pi, the density is given in the problem, 10 to the minus 3. This is slugs feet cube. Your velocity is given in 150 miles per hour. I need to convert that, but the conversion is given 60 miles per hour are actually equal to 88 feet second. And my b squared, this is 100 feet squared. So if you do the math, you can show that your downward velocity then is equal to 0.4521 feet second, which is the same as 0.31 miles per hour. Okay, so this is what we are really looking for in this problem. Let's conclude example number 1.